Okay, so electrical principles. We've got 3 exam questions. These are just some general things that hopefully you remember from the technician classes, or if you took my basic electronics course. You didn't, did you? You should have.
Going to offer it again?
Yes,
Then I will. I realize
September the 2nd.
maybe a little late, but I'm just in the show.
Well, I try to cover even stuff for the extra in it.
Okay.
You start with how electricity works and go all the way up to microprocessor.
Right.
Okay. The elementary charge is the charge for proton or electron. We talk about free electrons and stuff. That's how much energy we're talking about that makes it a positive ion or a electron, which would be a negative ion. And that charge is what gets, the flow of that charge is what we call current. So there's 6.24 times 10 to the 18th of those charges in 1 coulomb. And a coulomb is the amount of charge stored at 1 volt at 1 amp per second. You don't necessarily need to know that. So current is the flow of charge of 1 coulomb per second, and we measure it in amperes, named after James Ampere. And all these things are named after dead people. Well, except for E. We use E to represent the electromotive force, voltage. We measure it in volts and use the D sign for volts. And formulas, we represent it with E, electromotive force. Otherwise, we use capital I for current when we do a formula, like in Ohm's law. E equals I times R. And R for resistance, which we do in ohms. Frequency is the rate at which a current changes direction. We measure that in hertz after Heinrich hertz. And that's why it's capital H. There's a test question which will fool you if you don't get the capital box.
Speaker box.
And then one of the most important things, little c, which is the velocity of light in free space, which is approximately 300 million meters per second. And we only use the 300 in the calculations. It's close enough because it's actually 299.9 and something. We use the Greek symbol lambda to represent wavelengths. So a lot of times you'll see lambda over 2 or lambda over 4, half wave, quarter wave. We define resistance as the opposition to current flow, whether it's AC, DC, or RF. Pure resistance doesn't matter. It's not frequency dependent. We use L to represent inductance. And inductance is the ability to store electromagnetic energy, and we measure it in henries. Whereas capacitance, we use C. It's the ability to store electrostatic energy. A AC waveform is composed of electromagnetic and electrostatic fields, and they're 90 degrees opposed right on. Most of the propagation stuff deals with electrostatic fields, but when you get to inductance, it's the electromagnetic field, so it's storing that energy. And in a capacitor, we're storing the electric field. Reactance, we use X. That's opposition to AC current flow in an inductor or capacitor. that's the frequency dependent part of impedance, which is next. And we use Z to represent impedance, which is the opposition to AC current flow. Then we measure both of those in ohms. Impedance is actually the vector sum of the real resistance plus the reactance, which we'll show in the chart later. So we have three groups. The first one, you'll get one question about one of these things: reactance, inductance, capacitance, impedance, or impedance matching. Group B, we did decibels, series and parallel circuits, electrical power, sine wave RMS. You might need a calculator unless you're good at multiplying by 0.707. And PEP calculations, which is one of the other ones you might need to calculate. Also in the decibel, there's a question you hope you don't get, but they kind of do a reverse decibel, and they'll want to know for a 1 dB loss, what's the percentage loss? The answer is 20%. If you remember that, you don't have to calculate. And then the last one, we talk about resistors and capacitors and inductors, some of their characteristics and transformers. Stuff. So what is reactance? It's, like I said, it's the opposition to the flow of alternating current in an inductor capacitor, or something that has inductance or capacitance. In the real world, most things have both. We measure it in ohms. Then the formula for inductive reactance is 2 pi times the frequency times the inductance. And if we use inductance in microhenries, we can use the frequency in megahertz to make it simpler so you don't have a lot of zeros. Same with capacitive reactance. The difference is it's 1 over 2 pi times the frequency times the capacitance. So it's a reciprocal function, and it's nonlinear. The main thing to remember, and it is a test question, that inductive reactance increases with increasing frequency. Capacitive reactance decreases with increasing frequency. There's a chart showing, and because the capacitive reactance is a reciprocal, see, it's not a linear curve. Whereas inductive reactance is a straight line. So it's 2 pi times the frequency is somewhere on this line times the inductance. I don't know where I stole this chart from, but it's wrong. I fixed it here.
Okay. My nose is not recovered from surgery yet.
So when you get past the resonant point, X of L is going to be greater than XC. I'm not sure why they did that, unless they're trying to explain if you operate a inductor above its self-resonance, it appears to be capacitive. Another test question coming up. So what is reactance? Anybody?
Reading the questions thoroughly. Opposition, season current.
Problem.
Yeah, problem.
Okay. Almost sounds good.
Bravo. So
So Why is A wrong? Because it says direct current. There's direct current doesn't have a reactance. These last two, it's reinforcement of the flow and not opposition. What unit is used to measure reactance?
B.
Ohms. Farads or capacitance, if I mentioned that. Current is amperes, and the reciprocal of impedance is Siemens. It used to be modes, which was ohms backward. And then they decided to honor this guy Siemens. Which of the following causes opposition to the flow of alternating current in an inductor? Reluctance is the sort of magnetic equivalence of impedance. Admittance is the reciprocal of impedance. And I forgot what conductance is. It's reciprocal something. You don't have to know what it is, it's just that it's a strong answer. Went too far. Which of the following causes opposition to the flow of alternating current in a capacitor? Answer is the same. How does an inductor react to alternating current? An inductor with alternating current. Remember the chart? The graph? Goes up, right?
Yeah.
As frequency goes up.
I thought I remembered it from the test ham study, but apparently I was wrong.
Inductance increases with frequency, capacitance decreases. Well, reactance decreases with impedance. How does the capacitor react AC? There's a good chance you get one or the other question. Think about what you can eliminate. There's two obvious ones.
Help me out, guys. I mean, I'm grounding here. All right. Thinking.
As the frequency increases, the reactance increases, or as the frequency
It's the opposite
increases,
of
reactance decreases.
opposite of an inductor.
Yes. Okay.
Inductance, reactance goes up, capacitive reactance goes down. And these two, amplitude has absolutely nothing to do with reactance. Strictly frequency dependent. Okay, impedance. It's the opposition to the flow of current in an AC circuit. So it combines resistance and reactance. So it's the total opposition to current flow. It's also, it's a test question. It's the ratio of voltage to current. Turns out it's not quite that simple because those happen to be complex numbers. But as far as the test is concerned, it's simply impedance is equal to E divided by I. So it's the sum of the resistive and reactive components, or R plus JX sub L, or R minus JXC. X sub L is the inductive reactance, X sub C is the capacitive reactance, and we throw in J. Is everybody familiar with J? Okay, mathematicians use I as the square root of -1. Now, we've already used I for current. So engineers use J instead of I. So in these formulas, if it's in an engineering text, it's going to have a J, which represents the square root of -1. Because the reactance, because of the phase difference, it's going to be on the complex plane. So I think it's on the next chart, I can show you that. But you can actually do a vector plot where resistance is going to be on the x-axis and reactance is going to be on the y-axis, which is the complex axis. And admittance, and there's one question about that you might be getting. It's the reciprocal of impedance. It's just 1 over Z. Okay, here's the imaginary and real axis, and we've plotted a resistance and the sum of the inductive and capacitive reactances, because capacitive reactance is negative, inductive is positive, so when you add them together, it's the difference. Okay, so you would plot the difference, and the impedance value is either stated as Z impedance is equal to R plus JX minus, or the magnitude of this line, which if you remember Pythagorean theorem, okay, C squared equals A squared plus B squared. So this side is going to be the square root of R squared plus X squared. And that's going to give you the magnitude, and we talk about that magnitude at a phase angle. You don't get that until the extra exam. So as far as the general, you just need to understand what impedance is, and it's a combination of real resistance and reactance. So what happens when inductive and capacitive reactances are, I guess I missed talking about something here. Let's back up. Stick another chart. Forgot on this one. We're showing the fact that the inductive and the capacitive reactances cross at this point, and that's where that LC circuit would be resonant, because they cancel one another out. So all you have at that point is pure resistance. And that's the definition of a tuned circuit, when the inductive and capacitive reactances are equal. Okay, so what happens when the inductive and capacitive reactances are equal in an LC circuit? This one needed. I need to add a chart. This one needed more explanation. It's going to be C.
Well, I had a 50-50 shot at being right.
Because when you cancel out the reactances, all you have left is your resistance. So if it was a series LC circuit, you're going to have a resistor in series with 0 ohms. So it's going to be whatever the resistance value is. It's going to be much lower than when it is off resonance, where you have some impedance. If you had a parallel LC circuit, we hadn't got to it yet, you're going to treat the reactances like you would a parallel inductor. So it's going to be the reciprocal of the reciprocals. So you wind up having a very high impedance in parallel with whatever the resistance is. Hopefully that's what occurs in an LC circuit at resonance. This one should have been first. When it's resonant, what happens to the reactances? Okay.
How'd they cancel?
They're equal and opposite because capacitive is negative, inductive reactance is positive. If they're equal, opposite sign, then at pure resonance, they would be 0. So you're only going to have whatever resistance is in the circuit. And that's true whether it's parallel or series. It's going to be whatever the actual resistive value. So even if it's parallel, where your LC circuit is going to be very high impedance, it's a high impedance in parallel with that resistor. So the value is essentially going to be whatever the resistance. Okay, what is impedance matching? And why do we care? Matching is matching the source impedance, your transmitter, whatever your source is, typically your transmitter, to your antenna, which is the load impedance. Now, this applies to other things besides amateur radio, so it wouldn't have to be a transmitter or an antenna, but the basics still apply. In order to get the maximum power transfer, okay, you want to have the source impedance equal to the load impedance, and that assumes that the connection between them has the same characteristic impedance. So if we're looking at a typical transmitter, it's going to have a 50 ohm source impedance. So we would like the antenna to have 50 ohms. That normally doesn't happen. And the transmission line, whether it's coax or twin lead or whatever, needs to be the same impedance as source and load. Now, because that rarely happens, you have to have some way to match those impedances. You're kind of stuck with 50 ohms on the transmitter. You can play some with the antenna, like on a dipole. If you start dropping the elements, it will lower the impedance. It was normally about 72 ohms, and you can get it down in the 50 or below range, depending on the angle. Or you can use, or you can use a matching network, typically a transformer, a toroid, and you adjust the turns ratio to get the impedance ratio you need. So if you had a 50 ohm transmitter, your antenna was 100 ohms, you'd need an impedance ratio of 2 to 1. And we'll get to that in a little more detail coming up. You can use like Byron's big black box over here, which is that a pi or an L?
See, I believe it's pi, it's two tuning capacitors.
Okay.
So,
Some form of LC network to match it, and you actually adjust that to the opposite inductive and reactance that you see on the load. So it cancels it out. You try to. And it's normally a pi network, which would be 2 capacitors across the line with a series inductor. And on some of them, you can vary the inductance of the inductor. And on both cases, you can vary the capacitance. Or sometimes it's an L network with just an inductor and a capacitor. Or it could be a T, where you'd have the T, inductor, capacitor, capacitor, inductor. I don't know. One or the other. Bottom line is transformers, LC networks, or a transmission line transformer, which would typically be a quarter wavelength stub of transmission line at the frequency you're trying to match. So that's very frequency dependent. Whereas the transformer is going to be much more broadband.
so tune the antenna right the first time.
Yeah, and even though they call these antenna tuners, they don't tune the antenna. It's a matching network. To tune the antenna, you have to actually physically go change the length or add a capacitive hat or something to the antenna. This is at the transmitter end where you're feeding.
I love my first 40-meter beam antenna that was adjustable motor length on the driven elements.
Okay.
That was pretty cool back in the early 60s.
Well, I guess basically the screwdriver does that too, right?
Yep.
Because it just adjusts the coil.
And then the step IR check this reading element. There's step has a vertical, and then someone else has vertical, 2 similar groups. England makes one with wires.
Is Tar Heel a good one for me to use?
Huh?
Is the Tar Heel a good one to use?
I don't know. Ask him.
It generally gets Yankee, they talk about Yankee radio. That way I've already got the control ready.
My AC 991 will control through the controller and that target.
Okay, good.
Yeah, manufacturers tend to do that, and they make things that kind of work with their products and not necessarily other. This is a little chart showing power transfer. So if you're perfectly matched, and I had 50 ohms at the source and I had a 50 ohm load, I'm actually only going to get 50% of the power. They lost half of it at the transmitter end over the source impedance, and then the other half at the load. So the best you can do from point A to point B is 50%. So what is the term for the inverse of impedance? So it's way back there. Remember the inverse, reciprocal? Be 1 over the impedance. Right. No. Impedance. 1 over the impedance. There's only one question about this question. You may not get. What is impedance? Yeah, I kind of surprised me on this one.
Boy, I'm gonna say, ratio.
Yeah.
Or is it current to voltage?
Yeah.
It's one.
That's not what you would normally think of, but it's the only correct answer.
Voltage, okay.
I'm trying to remember the formula. I was like, yes, it's kind of Ohm's law, except you're actually going to be dealing with complex numbers. You actually try to plug in E and I.
I'm a simple guy,
Huh?
but I'm a simple guy.
But it is the ratio of the voltage to the current. You know. So which of the following devices can be used for impedance matching at radio frequencies?
All of it.
All right. Got your first, all the above. What letter is used to represent reactance? Reactance. Not impedance, so you can eliminate one of those, right?
Yeah. Yes.
And we didn't talk about B, which I think is, I think that might be susceptance or one of those weird ones. So we got X and Y. I don't know what Y is. So what's that leave?
My original answer, B, X.
Okay. So what did we learn? That reactance is the opposition to alternating current flow in inductors and capacitors. Inductive reactance increases with frequency. Capacitive reactance decreases with frequency. At resonance, the inductive and capacitive reactances are equal and opposite. In a series tuned circuit, it's at the lowest impedance when it's resonant. Parallel circuit is going to be at its highest impedance. In both cases, it turns out to be whatever the series, whatever the resistance is in the circuit. And the formula for resonance, which just for information, is 1 over 2 pi times the square root of the product of the inductance and capacitance. And keep seeing this 2 pi f pop up all the time in these formulas. And in engineering school, we learned that 2 pi f is represented as omega, which is the angular frequency. So angular frequency. That's where the 2 pi comes in. There's 2 pi radians in a circle.
Yeah.
Okay. So to make math easier, you represent a circle as 2 pi radians. Okay.
What I know.
So every waveform or every cycle is a complete 2 pi radians.
Right.
So you're doing F rotations per second of all the way around the circle, 2 pi radians. So that's where all those things come from. When you're doing normal engineering math with omega, then you make it a lot simpler. You don't have 2 pi f all of it. It just makes the math easy. Okay, so we also learned that impedance Z was the opposition to AC current flow, the total opposition. And it was the vector sum of the resistance and the reactance. So the formulas are there. It's R plus JL minus JXC in ohms. The magnitude of the reactance is Pythagorean's theorem. It's the hypotenuse. So the length of that vector. And it's also the ratio of voltage to current. So there's three different representations of it. Admittance Y was the reciprocal of impedance. That's what Y is. You just have to know it's the reciprocal. And impedance matching is matching the source impedance to the load impedance for maximum power transfer. And you do it with transformers, matching networks, or transmission line stubs. We don't go into those until the extra. You get to see a Smith chart, which are fun.
Maybe what more you said.
I just,
Well, I learned how to do them in college, and it was
I just saw a
fun.
VNA,
One sense.
a VNA that did Smith charts.